Which neutral atom has a higher ionization energy, oxygen or neon? So ionization energy refers to how hard it is to remove an electron from oxygen or neon. So if you look on the periodic table, oxygen is right there, okay? And then you have some spaces, and neon is right here. So we're talking about a horizontal relationship. So it's going to be about protons in this case. So they're on the same horizontal row. Neon has more protons than oxygen. So the answer is going to be neon. Okay. So the first thing you say is neon. Okay. And then you say, according to Coulomb's law, neon has more protons, and this is the key word, pulling on the the second, we could say, energy level electrons. Creating a higher ionization energy, I'm going to say IE for short, and a smaller atomic radius. Now, at some point, I'm going to ask you to actually break out this Coulomb's law into really what it is. So another full explanation, and you're going to have to do this once on the quiz, would be to say, neon, according to Coulomb's law, which states that the force of attraction between two charged particles increases as the magnitude of those charges increase and as the distance between them decreases, neon has more protons pulling on the second energy level electrons, creating a higher ionization energy and a smaller atomic radius. Let's go ahead and draw a picture of both of these. Okay, so we're going to draw oxygen here, and we're going to draw neon here, hoping this will help you guys visualize it. Okay, we know that oxygen has 8 protons in its nucleus. Okay. So those electrons in the second ring might look like this. And neon has 10 protons in its nucleus. So those electrons are going to end up being a little bit closer. Okay. With this distance here, that being the atomic radius. Atomic radius really being a side effect of that pull. Now remember, we can think about ionization energy as being like gravity. Neon is just a larger planet pulling on those electrons. Okay, let's go through and do this one. Which neutral atom has a higher ionization energy? Lithium or sodium? So if we're looking on the periodic table now, lithium is here, and sodium we know is down here. So instead of talking about protons, although sodium does have more protons, okay, we're talking about electron to electron repulsion, and this effect really is greater, according to Coulomb's law. Okay, so which neutral atom has a higher ionization energy, meaning which one is it harder to remove an electron? And that's going to be lithium. So we're going to say lithium. Okay. And we say according to Coulomb's law, lithium's electrons experience less electron to electron repulsion. Another way of saying this is Coulombic repulsion, thus creating a larger ionization energy and a smaller atomic radius. So notice I'm talking about atomic radius when it's not really asking me about it, but it's always an afterthought. Okay, this is really that idea of shielding, and we can look at this right now. Lithium and sodium. Okay, we know that lithium has 3 protons in its nucleus, and it's got those 2 rings. It's going to look kind of like this. And we know that sodium has 11 protons in its nucleus, and it has those 3 rings. So it looks a little something like this, where this distance here is the atomic radius. Okay, so first off, we can see that 1, 2, 3. Actually, I'm sorry. This is the 3rd ring. It looks like this. So this would be the atomic radius. Okay, so there's the nucleus, and there's n equals 1, and there's n equals 2, and there's n equals 1, n equals 2, n equals 3. So you see this electron right here is being shielded by the n equals 1 ring, the n equals 2 ring, and n equals 3 ring. Whereas this electron right here is being shielded by just the n equals 1 ring. So this electron here is being pulled in by the protons. That's the ionization energy. Okay, but that electron is being repelled by these electrons. Okay, this electron is being pulled in by the nucleus. That's the ionization energy, or gravity. And it's being repelled, yes, by this electron, but by nobody else. So because there's less electron-electron repulsion due to less shielding, it's going to have a larger ionization energy and subsequently a smaller radius. Which species has a higher ionization energy? Remember, the ionization energy is the energy required to remove an electron. Potassium or the potassium ion? Okay, so we know that K is right here, and we know that way over here on the periodic table, okay, there's going to be, is it argon? There's a noble gas. Okay, there's Regina. Forget who it is. Okay, so potassium is going to have to lose that 1 electron to be like its nearest noble gas. So the potassium ion is actually going to be K plus 1. Now, when you're dealing with the ion, sometimes it can be really helpful to write out the protons and write out the electrons. Now, they both have 19 protons. Okay, but potassium, when it's neutral, okay, has 19 electrons, and when it's plus 1, has 18 electrons. This is neutral. Okay, this has a charge, but this, because it has 18 electrons, which mimics the electron configuration of the noble gas, is much more stable. So being neutral doesn't mean stable. We know when we put this potassium in water, it started flaming up right away. Okay, in this case, potassium now is stable, even though it has a positive 1 charge. So if we look at this, it can't be the proton effect because they both have the same number of protons. It's going to be the other effect, which is the electron-electron repulsion effect. Okay, I don't think I did a great job of talking about this in class, but if we look at this 19th electron is being repelled by all those other 18 electrons, whereas this 18th electron is being repelled by only 17 electrons. So who has the highest ionization energy here? K plus 1. And then we can say, according to Coulomb's law, okay, the electrons in K plus 1 experience less electron-to-electron repulsion. That's because there's only 18 electrons. It can't be, again, the proton effect. Now, yes, there is a larger proton-to-electron ratio, but it's the same force pulling from the nucleus. One is just pulling through more electrons. So K plus 1, because according to Coulomb's law, the electrons in K plus 1 experience less electron-electron repulsion, creating a higher ionization energy and a smaller atomic radius. And we can draw a picture of that here. It's kind of trickier to draw a picture of it, okay, because they both have 19 electrons, 19 protons, but let's try and do it. 19p plus. Okay. This one is going to have 1, 2, 3. And this one has 1, 2, And the third one out there is actually empty. We're going to do it dotted because it lost its electron entirely. So in reality, there's nothing even in that third one. So that's why there's less shielding in this case. Okay, so really this is the atomic radius. It essentially has only 2 energy levels. Or 3, I'm sorry. I think potassium's lower. Either way, I'm not sure, but you get the idea here. Which species has a higher ionization energy, fluorine or the fluoride ion? Okay, so if you look at fluorine here, next to it right here is neon. Okay, so fluorine has to just gain that 1 electron to be exactly like neon. So fluorine is F, that's neutral fluorine, and the ion is minus. So let's do the same little exercise we did. Both of these have 9. This one has 10, and this one here, I'm sorry, this one has 9, and this one here has 10. Okay, so again, it can't be the proton effect because they have the same number of protons. It's shielding. And in this case, the F- one has more electron-electron repulsion because there's simply more electrons. So which species is it harder to remove the electron? It's the one that has less electron-electron repulsion, and that's going to be fluorine. So F, okay, according to Coulomb's law, F has less electron-to-electron repulsion, creating a larger ionization energy and a smaller atomic radius. And if we were to draw this, F right here and F minus 1, F has 9 plus, and this has 9 plus, this has 2 rings. It's really hard to see. This has 2 rings, but it's just going to be stretched out even more because it's hard to tell, but there's going to be that 1 extra electron in there. So, and that's the atomic radius. A little hint, when you're doing things like this, I'll do a little bubble over here. If you have like X and X plus, okay, this always is going to have a higher atomic radius than that. And if you have Y and Y minus, this is always going to have a higher atomic radius than that. And that sometimes is easier. It's easier for people to get at the atomic radius piece because more electrons, it makes sense that it's larger. And if there's less electrons, it makes sense that it's smaller. Okay? But then as long as you back into ionization energy, so if you say it's got more electrons, okay, which gives it more electron-electron repulsion, making the ionization energy smaller and the atomic radius bigger, that works. Or if you say it's got less electrons, like in X plus there, which means it has less electron-electron repulsion, which gives it a higher ionization energy and a lower atomic radius, that also works. Okay. Draw the PES diagram for boron and carbon on the same axis. So before we do it, let's just write the electron configuration: 1s2, 2s2, and carbon, 1s2, 2s2, 2p2. And we're going to draw our axis here. This is the relative number of electrons compared to one another, and this is the ionization energy. Sometimes you're going to see this called the binding energy. Let's call this side high and this side low. Okay. So we're going to do boron normally. There's the 1s2, little space for the energy level, 2s2. Okay, that's boron. Carbon, we're going to do with a dotted line. Now, carbon in this case has a higher ionization energy than boron because boron is here on the periodic table and carbon is here. So yes, there's more electrons there, but carbon has more protons pulling on that second energy level. So carbon's is going to be shifted more to the high side. So carbon's 1s2 is going to be over here. Carbon's 2s2 is going to be there, and carbon's 2p2 is going to look something like that. Draw the PES for boron and aluminum on the same axis. So boron, again, 1s2, 2s2, aluminum, 1s2, 2s2, 2p6, stable, 3s2, 3p1. Okay, so let's draw our axis. Let's stay with this being ionization energy or binding energy. This is the relative number of electrons. We'll call this high. We'll call this low. There's 1s2, 2s2 for boron. Aluminum now, in this case, we've moved up to a new energy level, so there's now all these extra electrons. So there's more electron-electron repulsion, making the ionization energy of aluminum less, meaning it's easier to snip off this electron, making its radius bigger. So aluminum now is going to be shifted everything to the lower side. So aluminum's 1s, and it just depends on what side you put this on. There's aluminum's 1s2, there's aluminum's 2s2, there's aluminum's 2p6. Okay, there we are. And then you can imagine we'd go over here. It's hard for me to draw it. I probably should have extended this. Okay. And then we're going to go to a new energy level. And it's 3s2, and there's the 3p1 with aluminum. But again, it's got a lower ionization energy, so just pay attention to the axis. In this case, it shifted left because it was less. And in this case, we shifted it to the right.